All right, what we're going to try to do today is review chapters 10 and 11 for an exam next Monday. Yeah, on the 12th. And we're going to go to that review document. Actually, there were two of them. Two review documents, but I spliced them into one, so I wouldn't have to switch. But the numbering scheme is exactly the same. All right. So, number one in the chapter 10 easy section, which of the following should have the lowest boiling point? All right, we've got sodium sulfide, hydrogen fluoride, ammonia, and nitrogen, and water. So it's given out kind of early. From the airport.
Oh.
Yeah. Somebody reversed their engines, slow down. Okay, so when we're looking at the lowest boiling point, lowest boiling point means that the intermolecular attractions between the molecules, among the molecules, should be the lowest. All right, if we have any ionic compounds here, they're going to have very high boiling points. So that lets this one out, sodium sulfide. If we have any dipoles, then they're a little bit less, but they may not be the lowest. HF, ammonia, and water all have significant dipoles. In fact, water is the highest because it's got hydrogen bonding available. And ammonia, you remember from last semester, ammonia is like this, right? So it has a dipole like that, right? And HF, fluorine is the most electronegative element in the periodic table. And it's only got one bond, so it's going to be a dipole like that. That leaves nitrogen. Nitrogen is like this. It's perfectly symmetrical. It has no dipole. So what forces does it have available to it? No clue? London dispersion forces, the very weakest forces of all. So nitrogen should have the lowest boiling point. In fact, its boiling point is minus 195 degrees Celsius, well below any of the others. And let's go to number 3. When a water molecule forms a hydrogen bond with another water molecule, which atoms are involved in the interaction? Well, we know water looks like this, right? With a positive end here, excuse me, negative end there, negative end there, positive here, positive here. So whenever two water molecules approach one another, if they approach each other like this, right, there's no bond going to form because they're both positive. So you know that the only way that you're going to get a bond between two water molecules is like this. Okay. So the one that fits that best is B, a hydrogen from one molecule and an oxygen from the other molecule form the bond. Let's see, we've got several candidates here. I think we're only looking at the third one. Go to number 4. What do we have here? Well, we have hydrogen chloride I assume in gaseous state. So we should have a dipole that direction. Right? Which of the following statements are incorrect? Electrostatic interactions exist between the molecules. Oh yeah. Right? This is going to be negative, this will be positive, and you could have like that. That form that bond. So there are electrostatic attractions between dipole molecules. The molecules find the best compromise between attraction and repulsion. That's true also. They attract each other, but they can only get so close before you start to get this negative interacting with that negative. Or this positive is too close to that positive. So there's a balance there between how close they can get before they start to feel opposing forces. So B is also true. These molecules exhibit ionic bonding. See? No, they don't. There are no ions in there. They're all partial charges, not full charges. All right, so let's see. 2 of the above statements are incorrect. All right, so we got to go down to D and be sure D is not another one. All right, so for D, we have this molecule, OCS. Now, I'm not sure about the bonds here, but we can look at the dipole moments for each of the bonds. And carbon is more positive than either one of these. So we're going to have a dipole that direction and that direction. But they're not equal, right? Because oxygen is more electronegative than sulfur. So overall, we're going to have a dipole that direction. So you can get the same type of interaction with OCS as you did with HCl. All right, so the only one that's bad is C. All right. 6. Which best explains the following trend? If we go, notice these are all noble gases. Right? And the boiling points are 4, 25, 95. And this is in K. 125 and 170. So we know we can't have a dipole involved because they're single atoms, right? The noble gases don't form compounds typically. So what explains the difference in boiling points? They can't have ionic bonds. They can't have dipole bonds. The only thing left is London dispersion forces, right? So is this trend true for London dispersion forces? The answer is yes, because if we look at relative size, like helium's like this, neon's like that, argon's like that, krypton's like that, xenon is a monster. So what you're seeing is for these, this is one atom, is for larger atoms or larger molecules for that matter, the London dispersion forces are more significant because you still got that electron motion that gives you the instantaneous distribution in charge density. And with a bigger atom or a bigger molecule, you have the tendency to get wider separation of the charges. So the larger the atom or the larger the molecule, the more significant are the London dispersion forces. And that will increase the boiling point as you get bigger and bigger and bigger because the forces are stronger. In fact, I think helium is the lowest temperature we can get in significant amounts of a substance. I don't know of anything that's colder than liquid helium. Oh, so the answer is A. London dispersion forces explained. 7. Okay. Which of the following compounds has the lowest viscosity? The lowest viscosity. That is, it flows the easiest. High viscosity would be more like molasses in winter. So here, what we want, the lowest viscosity will occur with the substance that has the smallest intermolecular forces available. Right? Now, there are two ways to approach this. You can look at the molecule itself and say, all right, does that have dipole moment involved or not, which makes London dispersion forces, and that works. But probably the quickest way is to know that the viscosity decreases from liquid to gas. Right? So the viscosity of liquid is going to be higher than the viscosity of a gas. That means we can eliminate all but B and E. Right? So we compare nitrogen gas and hydrogen chloride gas. And then we can invoke dipole interactions. This one has a dipole. This one is not. So this one's the London dispersion. That tells you that nitrogen gas will have the lowest viscosity of any of those substances. All right, number 8. When a nonpolar liquid displays a convex meniscus, nonpolar liquid displays a convex meniscus, and we're talking about like that. So we know it's not water. Water goes the other direction. Which of the following explains this behavior? Well, you've got two different opposing forces. You got adhesive and cohesive forces. If the cohesive forces are stronger than the adhesive, by the way, the definition, of course, means that adhesive means that the substance is adhering to its container. So the forces attracting this substance to its container are adhesive. And the substance and the forces attracting atoms or molecules of the substance internally are the cohesive forces. So which one wins? If the cohesive forces are stronger than the adhesive, you're going to get this type of arrangement because you can look at it as there's a net repulsion of the substance from its container. We see that in mercury. In a mercury barometer in a glass tube, you'll see a convex meniscus. Whereas with water in a glass tube, you see the other way around. All right, so the one that explains that is B. The cohesive forces are stronger than the adhesive forces. These are stronger than the adhesive. Number 9. Which substance can be described as cations bonded together by mobile electrons? Remember our discussions of bonding with metals. We had two theories. One was the electron C model, and the other was, of course, molecular orbital. The electron C model says that you've got cations of the metal, and then you've got all these electrons around here like that. That's the electron C model. That's what they're describing right here. Cations bonded together by mobile electrons. These are mobile electrons. So we're talking about a metal. Any of those a metal? Yeah, in fact, there's only one. That's A. Silver. All right, now this is a very poor model for explaining metal behavior, but to answer the question, yeah, that's one historical model. The molecular orbital model is much more predictive. It gives you much more information about the metals than the electron C model. All right, number 10. Which of the following statements about steel is false? Well, let's see. Contains carbon atoms in the holes of its iron crystals. Is that true? Yep. It's an interstitial alloy. Right? The carbon atoms fit into the voids. Remember that the videos that talked about voids. That's where the carbon atoms fit into the voids. The presence of carbon ion bonds in the alloy makes steel harder and stronger than pure iron. That's also true. When you get carbon and iron bonded together in those voids, it tends to lock the crystals in place. Pure iron you can scratch with your fingernail because it's a metal and it's soft, it's malleable. But if you put the carbon in there, it stops those crystals from moving. That's another way of explaining B. Pure iron is relatively soft and ductile because it lacks directional bonding. That's also true. And the amount of carbon directly affects the properties of steel. Yep. You've heard of low carbon steel, high carbon steel. So the amount of carbon does affect the properties of steel. That means all of them are true. E is the answer. Eleven. Which of the following statements is true about P-type silicon? Well, if we look at silicon and we're going to dope pure silicon so we can make a semiconductor. If we want a P-type, we need to dope silicon with something that has one or more fewer electrons in its valence shell. So that means what direction from silicon? If we go to the right, those are extra electrons. If we go to the left, those are deficient electrons. So we need to dope silicon with something to its left, like boron, aluminum, gallium, even indium has been used. So these to the left are deficient in an electron. That gives the P-type. P-type. I don't think it has a plus there, does it? That gives the P-type semiconductor. Deficient in electrons. Okay, so it's produced by doping silicon with phosphorus or arsenic. No, because those are to the right. They have extra electrons. Protons are the mobile charge carriers. I don't think so. Protons never move. Not in chemistry, anyway. Protons, yeah, I should take that back. When we get to acids, study of acids, protons do move. But not in this case. They don't carry the charge. It does not conduct electricity as well as pure silicon. No, it's a semiconductor. Pure silicon is an insulator. So if we dope it with either this side or that side, we create a semiconductor. That is, it conducts electricity under our control. That's the key to semiconductors. So all of those are false. None of them are true. About 14. Solid crystal sodium chloride is, yes, solid sodium chloride. We have an ionic substance that is bound in 6 directions with opposite ions. So the sodium will have, the cation will have 6 anions bound to it, but each anion will have 6 cations bound to it. It's a crystal matrix. And the solid crystals are very strongly bound to each other. The ions are bound to each other. They cannot move. So that means it will not conduct heat. It will not conduct electricity. And it's hard. Right? So if we take our examples here, the first thing, soft or hard, it's hard. So it's either B or D. Right? Then we go to the next one. B or D, high melting, high melting. Those are both correct. Then we go to the third position. Good electrical conductor, poor electrical conductor. It's a poor electrical conductor because the ions cannot move. You got to have mobile ions to conduct electricity. So D is the answer. So how do we get those ions to move? Well, there are only 2 ways I know of. You can melt it, right? Heat sodium chloride up so hot that it turns into a liquid. Or you can dissolve it in some solvent like water. Now the ions are free to move. Number 15. Which of the following has the highest melting temperature? Right. Again, we're looking at those molecules that are polar. In other words, they have a dipole. They would have a significant melting point. Those that are nonpolar would have a lower melting point because all they have available is London dispersion forces. But the highest melting point of all will be the ionic compounds. And there's only one ionic compound in that group, magnesium fluoride. So D is the answer for 15. 16. Which of these statements is false? All right, let's see. How about A, diamond? Is diamond a covalent crystal? Well, it's definitely a crystal. There's a regular arrangement of atoms. Are they covalently bound? Oh, yeah. Yeah, they're bound in a tetrahedral matrix. Right, so A is true. Diamond is a covalent crystal. How about B? The size of the unit cell of lithium and cesium is the same. This one's true. Lithium versus cesium in their unit cell. All we need to know here is relative size. So we look over here at the periodic table. Lithium is way up there at the top. Cesium's down at the bottom. They're both alkali metals. And they would tend to form the same type of unit cell. But since cesium is much bigger than lithium, the unit cell is going to be bigger too. All right, so the size of the unit cells are not the same. B is false. And since E says none of the statements are false and we found a false one, then we can stop. B is the answer. That is false statement. (17) How would you expect the melting point of carbon tetrachloride to compare with that of sodium chloride? Carbon tetrachloride and sodium chloride. Melting point. The melting point here should be exceedingly greater than the melting point of carbon tetrachloride. First of all, this is an ionic compound, and this is a nonpolar molecular compound. But it looks like the answers want an explanation. So let's see A. It should be lower because, yes, carbon tetrachloride should be lower because sodium chloride forms an extended ionic crystal lattice where carbon tetrachloride is covalently bonded small molecule. That's a pretty good explanation right there. Let's see, A is pretty good. How about B? It should be similar. No. Should be higher. No. Should be higher. No. E, it's not possible to say anything. All right. So B through E, we throw out. A is our best answer. All right, let's move on to 19. At normal atmospheric pressure and a temperature of 0 degrees, which phase of water can exist? All right, so if we've got water at 0 degrees Celsius and 1 atmosphere pressure, what phases can exist? Remember our diagram of, let's see, pressure and temperature? It went down like that, this, like that. And this is solid, liquid, gas. So along in here somewhere, we've got 1 atmosphere pressure. And the temperature at that point will be 0 degrees C. So at that point, what can exist at the same time? Along these lines, you can have 2 phases. In this case, solid and liquid. So we can have ice and liquid water at the same time. So A is the answer. There's only one point here, right there, the triple point, where you can have all 3, solid, liquid, and gas at the same time. Or if you're on this line, at any pressure temperature combination on that line, you can have liquid and gas. All right. That was 19. How about 20? Which of the following processes must exist in equilibrium with the evaporation process when a measurement of vapor pressure is made? All right, so if we're measuring vapor pressure, we've got a sealed container with a liquid here, and the gas, the same substance as the liquid, but in gaseous phase. All right, so we've gone from here to here as evaporation, but it's in equilibrium. If we want to measure the vapor pressure, this one has to be in equilibrium with this one. So what's this one called? It's called condensation. That's E on our answers. All right, 21. You're given the following boiling point data. Which one of the liquids would you expect to have the highest vapor pressure at room temperature? So remember, vapor pressure, or let's do it this way. Vapor pressure is inversely proportional to intermolecular forces. So it's proportional to the inverse of intermolecular forces. That is, as the strength of attraction between molecules increases, the vapor pressure is going to decrease. So if we're looking at the highest vapor pressure, we want the lowest, we want this to be the highest, we want the intermolecular forces to be the lowest. So we look at our possibilities here. Water, we have to let water out because it has a hydrogen bonding available. Methanol has hydrogen bonding available. And if we look at the data, we see that the boiling point is going to be an indicator of the strength of boiling point is directly proportional to the intermolecular forces. Right? So if we want the lowest value here, we want the lowest value there. Lowest boiling point means lowest intermolecular forces. So lowest boiling point would be diethyl ether, right? D. Diethyl ether would have the lowest boiling point, have the lowest intermolecular forces, which means the highest vapor pressure. Okay. That's the way we reason that one out. Oh, there's Kathy. Some folks are getting a late start today, it looks like. 22. Which of the following decreases as the strength of attractive intermolecular forces increases? All right. That's another way of saying 21. So 22 means as the strength of intermolecular forces increase, the vapor pressure would decrease. So that's why E is the answer for this one. Right. Same type of reasoning. 23. In which of the following processes will energy be evolved as heat? All right. So if energy is evolved, that means delta H is negative, right? It's exothermic. So we look at these processes and say, which one's exothermic? How about sublimation? Sublimation is going from solid straight to gas. Right? It absorbs energy to do that. So this one has a delta H that's positive. It's endothermic. Crystallization. Crystallization is the best way to think of this one is oh, mine's gone blank. Shoot. Going from individual ions, right, from cations and anions.
Shame girl.
Like that. So this would be a gas. Can't think of the word. We're going to run across it again anyway. So in this one, it gives up a lot of heat. This is exothermic, right? You're going from disordered to more ordered, and that gives up heat. So crystallization would be a good answer for that. Vaporization goes from liquid to gas, and that one has to absorb heat to do that. And melting goes from solid to liquid, and it also has to absorb heat to do that. All right, so crystallization is our best bet for an exothermic process. All right, let's see. All right, we've got a phase diagram here, 25. Okay, so notice on this phase diagram, the solid, liquid, and gas regions are identified. The pressure and temperature axes are labeled, and we're given a 1 atmosphere line across the middle. So anywhere on that line, we're at 1 atmosphere. Okay, what's the question? The diagram qualitatively correct for water. We know that's not true. Why? That's false. Because the slope of the solid liquid is the wrong direction. It's positive slope. And for water, the slope between solid liquid should be negative. Should slope the other direction. Right, so we know A is not true. The diagram shows that the melting point of the solid increases with increasing pressure. So let's see if that's true. Increasing pressure And the melting point is going to be on that solid liquid line. Right? The solid liquid line right here shows us melting point at given pressures. So as we increase the pressure, we're saying that the melting point of the solid increases. So if we increase the pressure, what's happening to the temperature? It's increasing also. Right? That's a positive slope. So as we increase the pressure, we're increasing the temperature. So B is true. None of the above statements is correct. Well, we found our answer then. B is the answer. How about 26? This is a phase diagram for compound Q. You wish to purify a sample of Q that was collected. All right, maybe I better draw this one. Okay, so we have pressure on this one in atmospheres. We have temperature on this one in K. All right. Then we're going to go up to, let's see, we're going to go up to this point. Then we're going to get a line this direction. And this one is almost the same slope. Actually, it goes out here like this, like that a little bit. Okay, so this is solid. This is liquid. This is gas. And we've got right about here is 0.5 atmospheres. And right about here is 1 atmosphere. And here is 1.5. And then we've got 100 degrees here, 200 there, 300 there. Kelvin. All right. So conditions of the problem. Q was collected at 1 atmosphere pressure and 100 K. So this is where our starting point. That's where Q was collected, right there. 1 atmosphere pressure, 100 K. We want to purify Q by subliming it. So that means it has to go from solid to gas. It's either got to go this direction, or if we come down here, it could go this direction. But it's got to cross that line somehow. So let's see which one matches. Increase the pressure to 1.5 atmospheres, and then increase the temperature to 300. What'll that do? That'll take us from solid to liquid. That won't work. Right, so A is out. How about B? Increase temperature to 300 K from here, go to 300, keeping pressure at 1. That's going to go through liquid to gas. We don't want that. We want to go solid to gas straight, directly. Right? So we can't do that one. How about C? Lower the pressure to 0.5. Okay, so we're coming down to here. Then what? Increase temperature to 200. Then we go from here to 200. That'll do it. That'll sublime solid to gas from there. So C is our best answer. We found our best answer already. Okay. Right, 26. Yeah, skip a few of those phase. How about this one? 29. Notice anything funny about this one? The solid to liquid phase is negative slope. Where have we seen that before? Water. Oh, yeah. Yeah, water. In fact, I've been searching the internet, looking at sources, try to find another negative slope, solid liquid. I can't find one. At this point, water's it. So Given the phase diagram below, which of the following statements is false? The solid has a higher density than the liquid. If this is water, the solid has a lower density than the liquid. That's why ice floats in liquid water. So A is definitely false. At some constant temperature, the gaseous substance can be compressed into a solid and then into a liquid. Yeah, right. If you went to this place right here, let's take that for example. If you went right here, then you could increase the pressure on that temperature and go from gas to solid and then to liquid. All right, so B is true. In fact, A is the best answer. None of the above is false. No, A is definitely false. If that is water, then it has to be A. All right, now we're going to go to moderate difficulty. And we start numbering again. Which of the following is the, let's see, get that out of my way, is the correct order of boiling points for KNO3, KNO3, CH3OH, which is methanol. That's the one you don't drink. And then C2H6, which is ethane and neon. Okay. Correct order of boiling points. So the boiling point is going to be highest for the one with the strongest intermolecular forces, which would be this ionic compound. Right, so its boiling point is going to be highest. And notice that all the answers have carets pointing to the left, which makes the right-hand side bigger. So the highest one is going to be KNO3. Right? How about the lowest one? Lowest one's going to be neon, right? Because it has London dispersion forces are it. Right? Then in between, we have the next strongest is the one with hydrogen bonding. And that leaves ethane as a non-polar organic compound, but it's a larger molecule than neon is an atom. So what did we say earlier about the size? When London dispersion forces are involved, the bigger the size, stronger the forces. So that would be D. D would be the best answer. All right. Scroll down to 4. Go. Assume 12,500 joules of energy is added to 2 moles or 36 grams of water. So we know that we have water, we have 2 moles, which is equivalent to 36 grams, 36 grams of water. Close, 36.04. Anyway, and the energy input is equal to 12,500 joules. Okay. The molar heat of fusion is 6.02 kilojoules per mole. All right. So we're taking water through various phase changes and increases in energy content. And we want to find out what is the phase. I mean, is there only one phase at the end of this heating? Are there 2 phases if we end up exactly on a phase change line? So what's left over? If we look at it this way, remember the stair step, right? This is heating progress to the right. So we're adding heat that way. And this is the temperature exhibited by the substances. Right? In our example, we had minus 20 went up to 0, and then we went up to 100. So from here to here, we're heating the ice. Okay, when we get to 0 degrees, the ice starts to melt. And this is all at 1 atmosphere. Then the ice begins to melt. And when all the ice is melted, now we're heating the water to 100 degrees. That's a little above 100, isn't it? To 100 degrees. Right? Then we boil the water. And as soon as all the water is boiled, all the liquid's gone, now we're heating the steam. So down here we have only solid, here we have only liquid, and here we have only gas. But in here we have solid and liquid, here we have liquid and gas. So here in these sections right here, we learned last semester in calorimetry that the specific heat of the substance determines how much heat is required to raise the temperature. All right. So what are the conditions? Well, we're starting at 0 degrees. Right? So we're starting right here. We don't have to deal with this part. Right? Our ice is at 0 degrees, and we're going to add heat to it. So what's happening now? All the heat is going into melting the ice, not raising the temperature. That's where the molar heat of fusion comes in, 6.02 kilojoules per mole. So this first step right here is 2 moles of water. How much energy is required? 6.02 kilojoules per mole, 6.02 kilojoules per mole. So this is melting. Oops. Try that again. Melting ice. That's what we're talking about here. And that's, let's see, 12.04 kilojoules, right? Because the moles cancel. Well, our values are in joules. So how much heat do we have left? When we get to this point, we've got 12,500 minus 12,040 joules. Right? So that's what, 460 joules left over. All right, so now this amount of heat is going into raising the temperature of liquid water. And you remember the formula for that one? Excuse me. The specific heat, right, for water times its mass, excuse me. Sorry. Delta H. Specific heat of water times its mass times the change in temperature. Okay. So our specific heat of water is 4.18 joules per gram degree C. The mass of water is 36 grams. And we have final temperature minus initial temperature, which is 0, right? Starting from 0. Okay, so we just have to solve. We know that this is all the heat that's available, 460 joules. That's all that's left over. So if we solve this temperature, right, where's my calculator? If we solve for this temperature, we say that's 0. So we just need to say 4.18 times 36 to give us that factor. And this factor right here is, let's see, 150 0.5. Grams cancel. And this is joules per degree C times this temperature. Okay. So the final temperature is going to be this one, which is in the numerator here, goes in the denominator. 460 joules divided by 150.5 joules per degree C. Joules cancel. Remember, the denominator of the denominator is the numerator. So this one in the denominator here becomes the numerator. So I need 460 and divide that into it. I get about 3.1 degrees. All right, so that's the final temperature with this amount of heat available. Where is that going to be? Well, it's going to be right down here. Right. There's nothing but liquid. Liquid only. So C is the answer. Okay. This is one of those that helps draw a picture. Does everybody got what they need? Okay. Let's scroll down a little bit, see what else we can find. Okay, now we're into difficult. And we start numbering again. So a crystal was analyzed with X-rays having 2.33 angstrom wavelength. The wavelength of our X-rays is 2.33 angstroms. Now, what's an angstrom? We ever talk about an angstrom? All right, an angstrom, 1 angstrom is 10 to the minus 10 meters. The angle of the first order diffraction when n equals 1, then theta equals 19.2 degrees. What we want to know is for the second order, what will be that angle? We're looking at the Bragg equation here. Right? If we go to the very end, get this out of the way. If we go to the very end, we'll find the Bragg equation. And remember, useful information, anything in useful information will also be on the exam. So there's the Bragg equation. Bragg says that n times lambda equals 2 times the distance separating the layers in the crystal times sine theta. All right. Now, there are two ways to solve this problem. You can insert this value, put 1 here, you can put 2.33 here, and you can put 19.2 here and find out what that distance is. Okay? And what are the units going to be? The units are going to be the same units as the wavelength. They're going to be in angstroms. D will be in angstroms. That's one way. And then once you find out what the distance is, you go back and substitute a 2 here, the same wavelength, and the distance here, D, in angstroms that you determined from the first calculation, and then solve for theta. Right? That's the long way. The short way is to use a little algebra. For n equals 1, if we solve one thing, actually there are two things in common. The wavelength is the same and the distance in the crystals between the crystal layers is exactly the same. So if we solve this equation for D, right, that's n lambda over 2 sine theta. Right, I took this 2, this sine theta, and put it over here. Right, so that's D. Then what we can do is say, since the distance is the same, right here, then this one, 1 times 2.33 angstroms over 2 sine, if this is 1, this is 19.2 degrees, right? Then on this side, we have 2 and 2.33 angstroms. And then we also have 2 here, and we have sine unknown theta. See what I did? Right, I've got those 2 equations. They're both equal to the distance between the crystal layers. So the only thing that changed in this whole setup is sine theta. We can solve for sine theta. All right. This is the same on both sides. It goes out. All right. This is the same on both sides. It goes out. So now we have D on this side. We have 1 over sine 19.2 degrees. And on this side, we have 2 over sine theta. Now we want to get sine theta in the numerator. So let's move this one over here and this one over here. Right? So 2 times sine 19.2 degrees equals sine theta. Did I do that right? Yeah, move this one over here with that 2, this one over here with that 1. So now we just need to know what sine 19.2 degrees is. 19.2, and let me find my, here's my sine. Right, so that's 0.3289 times 2. So this one is 0.6577 equals sine theta. How do you find theta out of that? Well, what's the mathematical inverse of sine? It's the arc sine. Right, so what we have here is this one, arc sine of that value will be theta. And if we go to our calculator, we find that all we need is a shift key, and arc sine is just above sine in your keyboard. So I've still already got that in there. I just say arc sine of that value is 41.1 degrees. Theta equals 41 degrees. So that should be the second order angle. And I need to go back to C10. Let's see, I went too far. There it is. 41.1 is B. Angstroms. Everybody remember algebra? I had trigonometry too. Because you got to do science. Has anybody not had trigonometry? Okay. All right. So your calculator will help you there. Sine theta, and anytime you need to do the reverse to find out what that angle is, use arc sine of this value.
The arc sine, are to -1?
No. Well.
On my calculator, where would I find that?
Oh, where did you find the arc sine? Okay. No, don't use -1. Let's see, sine is here. Oh yeah, sine to the -1. That's what they're calling arc sine.
Okay.
Yeah, sine to the -1. That's kind of misleading, actually. Because it's technically it's not an inverse. We used to have, before calculators, we used to have tables. And you'd look down the table on theta and find the sign.
So it's not giving me the same.
No,
Unless I'm.
0.6577.
Yeah. Is that him?
Oh, you know what? You may have it set up in radians. You need to set it up in degrees. Yeah, it's displaying, I think it's displaying in radians. You want degrees. You need to have set up your display for that.
So we have to go change it right here to degree.
Yes, there you go. Now try it. There you go. Yeah, be sure your output's set up in degrees, not radians. Does yours have it? Oh,
I know. Yeah.
radian's another way of expressing angles. Okay. Remember the unit cell? I mean, the unit, not the unit cell, but the unit circle. Okay. And this point is considered one value. So that'll be a +1, this will be a +1, this will be a -1. And you have this circle like that, and any angle here, if this length here is equal to this distance here, then that angle is equal to 1 radian. That's where it comes from. Not that you're going to need it, but if you're curious. All right, let's get back to business here. Chromium metal crystallizes as a body-centered cubic lattice. So we've got a body-centered chromium metal. So you're going to have a chromium here, a chromium here, chromium here, chromium here, here, and chromium here. And you're going to have a chromium right in the middle. Body-centered cubic lattice. If the atomic radius of chromium is 1.25 angstroms, right? So these are not going to touch because that one's in the middle. It's keeping them apart. So it's going to be like that. And this distance here, this radius, is 1.25 angstroms. 1.25 angstroms. Okay. What's the density of chromium in grams per cubic centimeter? So what we're after is the density of chromium in grams per cubic centimeter. So what do you need to know to find density? You need to know the mass and the volume occupied by that mass. So we need to know the mass of these chromium atoms here, and we need to know the volume of that cube. So what we're looking for is actually the distance here on the edge, that length. See, I'm not sure what they use in here. That length. Right? So body-centered cubic. Let's see what page is this. 12. So I can come back to the right page. If we go down to here we go. Body-centered cubic edge. Actually, there should be an equal sign in here. We're calling this A. This edge A is 4R times square root of 3. Times square root of 3. That's equal to our length. Okay? And go back up to 12 here. Here we go. All right. So this is going to give us the volume. All we need is that length, and we can cube it. All right. So why don't we let's see, the length on that edge would be 4 times 1.25 angstroms divided by the square root of 3. Right? So let's see what that value is. 1.25 enter 4 times and then square root 5. I get 2.887 angstroms is equal to the length of that edge of that cube. That's not correct. Should just be L. Okay. So before we cube it, why don't we convert it into centimeters? Okay. So let's make this into centimeters. What's an angstrom? Well, an angstrom is 10 to the minus 10th meters. And then we can convert meters into centimeters because it takes 100 centimeters to make a meter. So that cancels this one, cancels that one, and that one. So I'll give us centimeters. Let's see. That's 10 to the minus 8, isn't it? 10 to the minus 10 times 10 squared is 10 to the minus 8. So I get 2.887 times 10 to the minus 8th centimeters. Now the volume is going to be that value cubed. So I just say here, this is 2.41 times 10 to the minus 23 cubic centimeters. So now we got the volume. What we need is the mass. What's the mass? Well, how many atoms of chromium are in there? Remember? Each one of these chromiums is shared by 8 other cells. So there's only 1/8 in this unit cell. But we got 1, 2, 3, 4, 5, 6, 7, 8. 8 times 1/8 is 1. So there's 1 chromium from the corners and 1 in the body. So that's 2 chromium atoms per unit cell. Remember that from our lecture? So mass is going to be a calculation where we have 2 atoms of chromium. Now we just need to convert that to mass. And what's the relationship between atoms and mass? Let's see, chromium. It's grams per mole. So we need to know how many moles of atoms that is. 0.022 times 10 to the 23rd atoms per mole. That takes care of the atoms. Now we need to convert moles to grams. Right, and that was what, 52.00 rounded off. Grams per mole. So that'll give us the mass of atoms in that unit cell. All right. That's 2 enter and 6.022 exponent 3 divide times 52. And I get 1.7. That's 1.73 times 10 to the minus 22 grams. So we have grams, cubic centimeters. And the density then is, let's see, 1.73 times 10 to the minus 22 grams. That's the mass in that unit cell, and this is the volume of the unit cell. There we go. Now let's see. I just need to flip those and divide. So I get 7.2 grams per cubic centimeter. All right, 7.18. Yeah, 3 significant figures. What am I thinking of? It is 7.18. Okay. That's how it's done. And it all goes back to what's the question? Question is, what's the density? That means we need to know the mass and the volume. So we attack the volume, then we attack the mass. Then we put them together. Right. Run out of time. Okay. Oh, chapter 11. All right. Fortunately, this lab is not a particularly difficult one, and it shouldn't take a whole lot of time. Number 1. Okay. In a 0.1 molar solution of sodium chloride in water, which one of the following will be closest to 0.1? Molar. 0.1 molar sodium chloride, which means what? 0.1 mole of sodium chloride per liter of solution. Okay. All right, to make this quick, 1 liter of solution, at that concentration, there's not a whole lot of salt in there. So the volume, the density of water is about 1 gram per cubic centimeter, 1 gram per milliliter, or 1 kilogram per liter. So if we've got a liter of solution, we have approximately 1 kilogram of water, which is the solvent, right? And this is molality. So molality is going to be the closest to molarity. That's D. Now you can go in and calculate the rest of them you want. And I think I do that in some of my videos. But in the interest of time, that's what I had to take a shortcut. So get this out of the way so I can see what I'm doing. Number 2. Which of the following concentration measures will change in values as the temperature of the solution changes? any measure of concentration that uses only mass or only numbers, such as moles, will not change with temperature. The only one that changes with temperature is the one that involves volume. So mass percent, mole fraction, molality, those will not change. Molarity is the only one that changes with temperature because it has volume in its calculation. So D is the one that you don't want if temperature is going to change. All right. And 3, which of the following chemical or physical changes is an endothermic process? In other words, you got to put energy into it to make it happen. Evaporation of water. Yeah. If you go from a liquid to a gas, you do have to put energy in here. Delta H is positive. Well, E says none of these, so the rest of them must be exothermic. Combustion of gasoline, sulfuric acid and water mix, yeah, that's ectothermic. Freezing of water, when water freezes, it gives up heat. It goes from liquid to solid, becomes more ordered, has a more stable, lower energy profile, so it gives up that energy as heat. So A is the correct answer. Right? Evaporation of water is an endothermic process. Which statement about hydrogen bonding is true? Hydrogen bonding. Well, in order to have a hydrogen bond, some part of the molecule, it can be a small molecule or a large one, doesn't matter. You're going to have some element here that is either, well, let's see. Okay. It needs to be an electronegative element of oxygen, nitrogen, or fluorine. And then it's got attached to it a hydrogen. So any one of these will do. But when that happens, when the hydrogen bonding happens, which one is true? Hydrogen bonding is the intermolecular attraction between two hydrogen atoms. I don't think so. What happens is when you approach, when another molecule approaches, this is going to be slightly positive, this one's going to be negative. And if we get another one approaching, right, this is going to be negative, this is going to be positive. The attraction is between the hydrogen on one molecule and the electronegative atom on the other molecule. And in the interest of time, the only one that fits that is E. Hydrogen bonding arises from the dipole moment created by the unequal sharing of electrons within certain covalent bonds within a molecule. Right? Five. Which of the following favors the solubility of an ionic solid in a liquid solvent? This one's a little hard to follow. I'll have to admit. An ionic solid. So we've got a, let's see. Let's say a metal and a non-metal, an ionic solid. And we're going to put it in a solvent. That means this is going to be solvated, and this one's going to be solvated somehow. It doesn't say water, so I can't put anything in here. Goes into solution that way, separate ions. Which of the following favors the solubility of the ionic solid? Large magnitude of the solvation energy of the ions. The solvation energy is that draws these together with the solvent. A large value of solvation energy means that there's a strong attraction between those ions and the solvent. Yes, A would be true. That favors formation of the solution. a small magnitude of the lattice energy of the solute. The small lattice energy means it's easy to get these things apart. That's the one I was looking for earlier, lattice energy. If it's easy to get those apart, then they have the opportunity to interact with the solvent. So that's also true. Large polarity of the solvent. That's another way of putting these two together. If the polarity of the solvent is very large, then it has a chance to interact with these ions, right? The molecules are polar in the solvent, and we have a strong attraction between the positive side of the solvent and this one, and the negative side of the solvent and that one. So yeah, they're all true. Each one of it's true. That's D. All right. Six. All right. All of this is going to take some work. So do we have time for that? Let's come back 6 if we have time. So let me hold this one. C11. Actually, C11 is not easy. Number 6 is not easy. We'll hold that one and come back to it because it takes a lot of work to get to the answer. All right. Moving on to 7. Use the following drawing of a gaseous solute in equilibrium with a solution to help answer the following questions. Which of the following statements are true when the piston is pushed in or downward? Well, what happens? If we've got a gaseous solute and we decrease the volume, we're increasing the pressure, what happens to the solubility of that gas? It increases. You get more gas in solution if you increase the pressure of that solute in the headspace. So this will cause the pressure of the gas to increase and the concentration of the dissolved gas to go down. This is the way around. It should go up. Right? So we need one that says go up. It's either this one, C, go up, or this one, E, go up. So C would be, this will cause the pressure of the gas to increase, the concentration of the dissolved gas to go up. Yes, that's it, C. Yep. Number 7, C. Number 8. Which of the following correctly states the relationship between temperature and the solubility of substance in water? Well, we know that typically, if the substance is a solid, the solubility generally increases with increasing temperature. Not always. And we can't know without, it's empirical. We have to actually do the experiment to see if it's soluble at a higher temperature. Gases, though, we can say, as the temperature increases, the concentration of the gas in solution goes down. So which one of these fits? Well, C is a good one. Solubility of a substance in water with temperature cannot be accurately predicted, especially for ionic solids. That's true. Are gases mentioned in here? Solubility of substance in water increases, temperature rises. No, gases do not increase solubility. B doesn't work either. Right, so solubility D, substance in water decreases as temperature lowers. No, actually gases become more soluble with decreased temperature. Okay, so C is the best answer of all those. About 10. A solution contains 1 mole of liquid A and 3 moles of liquid B. Okay, we're looking at Raoult's law. And we're given vapor pressures for both of them, so we need the modified Reynolds law. So we're gonna have diagram like this. This is going to be increasing A. This is going to be increasing B. Right? So if it's 100% A, what we're going to have is a vapor pressure of, for A, let's see, this solution has a vapor pressure. Liquid A has a vapor pressure of 265 torr, which is millimeters of mercury, if you recall. If it's 100% B, if it's all B, then the vapor pressure is 355. Right? So the ideal solution would be between here and here, anywhere along that line. What we're told is that the solution that under investigation has 1 mole of A and 3 moles of B. So that means A is only 25% or 0.25 mole fraction. Right? So here's half, here's here. Right? So we're right in here somewhere. It's 0.25 A and 0.75 B mole fraction. All right. Okay, so far so good. We're given the actual vapor pressure of 314 torr. Right, so 314 torr down here somewhere, probably. We're going to have to use the Rayleigh modified law. So the actual vapor pressure of the solution is equal to the mole fraction of A times its pure vapor pressure plus the mole fraction of B times its pure vapor pressure. Right? So the mole fraction of A is 0.25. And its pure vapor pressure is 265 torr. And the mole fraction of B is 0.75. And its pure value is 355. Okay. So if this is ideal, the vapor pressure of the solution should be that plus that. So 265 times 0.25 is 66.25 plus 355 times 0.75 is 266. Yes. We'll add those together. And let's see, let's round it off to 3 significant figures. 333. That would be the ideal. So the actual value is less than the ideal. Right? So our deviation is negative. What causes a negative deviation? When there is a strong attraction between A and B, stronger attraction between A and B than there is of A to A or B to B, then you get a negative deviation. All right, so it's going to be down like this. All right, so which one of these fits the answer? This solution exhibits a positive deviation? No. B, this solution exhibits a negative deviation? Yes. The solution is not ideal. So B says a negative deviation. Okay. That was 10. Well, watch and see if they're still writing. And 12. A cucumber is placed in a concentrated salt solution. What will most likely happen? So we got our cucumber. With our seeds. And we're in a concentrated salt solution. Oops. Got it. Oops. Okay. So which way is the water going to move? The concentration of sodium chloride outside the cell is higher than it is inside the cell. So what does that say about the water concentration? The water concentration outside the cell is less than it is inside the cell. And since semi-permeable membranes only transfer water or small gas molecules, then which way is the water going to move? It's going to move toward the side where it has the lowest water concentration. Right, so it's going to move this way. Water moves out of the cells and they crenulate. They shrink. So the one that fits that is water will flow from the cucumber to the solution. Right? Okay. That was 12, 13. Osmotic pressure depends on all but which of the following? Let's see. We need the osmotic pressure is equal to molarity times the gas constant times temperature. Right? Okay. So it depends on the molar concentration, right? It depends on temperature, but it doesn't depend on what? Atmospheric pressure. A, it does not depend on pressure. Right. All right, 13, 14. Shaving cream is an example of which colloid type? Remember your colloid types? No? It's a foam. It's a gas suspended in a liquid. Emulsion. I worked with an emulsion several times this weekend. Scrambled eggs. Egg is an emulsion. And how do we, and that is we're talking about colloids here. And how do you destroy a colloid? Well, there are a couple of ways. You can either salt it out or you can heat it. So when I destroy the colloid in my egg, I heat it. I cook it. And it coagulates. It's no longer a colloid. All right. 11 moderate now. Let's see. Yep, start numbering again. Not with 1 though. We're going to skip down to 3. All right. A 0.2 molar solution of a solute X. 0.2 molar X in benzene. Okay, benzene is the solvent. Displays an osmotic pressure of the formula. I equals 0.1 times RT. So remember that sometimes we need the Van Hoff correction. The Van Hoff correction, what we've looked at so far, the Van Hoff correction would be this I times molarity times R times T. And what we usually the examples that were given in lecture were those that dissociate. So sodium chloride would be an I of 2. And calcium chloride would be an I of 3. Sodium phosphate would be an I of 4. But here's a twist. We also discussed ion pairing. So at high concentrations, these ions repair. And say for sodium chloride, instead of an I of 2, it might be a 1.8 for high concentrations because we get the pairing. And so when we decrease I, we're seeing pairing. Well, what do we got here? Well, this value associated with this value, we know that 0.2 is in. 0.2 molar times I is actually 0.1. So what would I have to be to give you 0.1? It'd have to be a half, wouldn't it? So in order to get a half, you're not dissociating, you're pairing. So this X, when you put it in benzene, it pairs up in two things, like you get an X in solution. All right. So what we're saying is that B, X exists in benzene as X2. It does that thing in benzene. All right. Number 4. Which of these solutions, 0.1 molal sodium chloride, 0.1 molal sodium chloride, and 0.15 molal glucose, or 0.1 molal calcium chloride would have 1 vapor pressure. We're talking about the highest vapor pressure. And 2, the lowest boiling point. Respectively. So which one of these would have the highest vapor pressure? The one that has not only the lowest attractive forces, but also that doesn't dissociate. This one has the effect of 0.2 because I equals 2. This one has the effect of 0.3 molal of ions. Put it that way, ions. And this one is just as is, because it doesn't dissociate. So the highest vapor pressure would be this one, right? Lowest concentration. This would be glucose. How about the lowest boiling point? The lowest boiling point would be the one with the weakest attraction and the lowest concentration in solution, right? 0.2 versus 0.15 was they're both glucose. So D would be the answer. This is a colligative property. We're looking at vapor pressure as a colligative property, so it depends on the concentration of the solutes. All right. I think I need those for 5 also. Say 5. Yeah. So we got the same set. Now we're looking at the lowest vapor pressure. Lowest vapor pressure. And the lowest boiling point. So we found the lowest boiling point already is glucose. Lowest vapor pressure, would be the one with the highest solute concentration, would be calcium chloride. So calcium chloride, C, calcium chloride, 0.15 mole glucose would be the answer to that one. All right,
I'll get down to difficult.
and we're gonna pick it up at 2. A solution prepared from 53.8 grams of a non-volatile, non-dissociated solute and 85 grams of water. The vapor pressure of the solution is 60 degrees. At 60 degrees is 132 torr. The vapor pressure of water at 60 degrees is 150 torr. What's the molar mass of the solute? All right, go to the question. What's the molar mass? I abbreviate MW for molecular weight. We need to know the mass per mole. All right. Do we have the mass? Yeah, we have the mass of that non-volatile substance, 53.8 grams. 53.8 grams. What we need to know is moles. Right? So how do we find moles? Well, we use a colligative property. The vapor pressure of the solution at 60 degrees C is 132. The vapor pressure of water is 150 torr. So we know that the vapor pressure is going to change with the molar concentration of the solute. Right? So, and this is a non-volatile solute, so we can use the simple Raoult's law. Right? So the vapor pressure of the solution is the mole fraction of water times the pure water vapor pressure. Right? So if we know that the pure water vapor pressure is 150 torr, and the pressure of the solution is 132 torr, then we can find the mole fraction of water. Right. So the mole fraction of water is equal to 132 divided by 150. Which is 0.88. Okay. Right, so that's the mole fraction of water. How many moles does that represent? Well, we've got 85 grams of water. Right? 85 grams of water. How many moles is that? What's the molar mass of water? 18.02, right? So 85 divided by 18.02 is 4.717 moles of water. So this is the mole fraction of water. What's the mole fraction of the substance? Well, the mole fraction of, let's see, does it give it a name? Doesn't say. So the mole fraction of our unknown is 1 minus 0.88 or 0.12, right? 2. Okay, let me see. We know how many moles of water. And the moles of water. Actually. Let's set X. X equals the moles of X. Okay. That means that the mole fraction of water would be 4.717 divided by X plus 4.717, right? And that's equal to 0.88. So we didn't even need this one. Follow me? Mole fraction of water is the moles of water per total moles. And the total moles has to include the moles of X. So now that we have this value, we can solve for X. All right, so we can have, well, let's see, it's going to take a couple of steps. So this one times that one, 0.88x plus 0.88 times 4.717 equals 4.717. So we just need to solve for X. So I'll multiply these and subtract from that side. 0.717 times 0.88 is 4.144. Subtract this from that side. Is equal to, so 0.88x equals 0.572. So X is going to be 0.572 divided by 0.88. Which is 0.6510. And X is equal to the moles of X. Okay, so now we have 0.65 moles. And we can calculate the molar mass. 53.8. And I get 82.7 grams per mole. Oops. It's kind of off, wasn't it? I made a mistake, calculation error somewhere. Was it this one? 132, 50, 150. 32. Okay, those values are correct. That's 88, that's correct. So did I do this one right? 85 grams of water. 18.02 divide 717. That's right. Okay, so 717. How about 0.8? 4.717 enter 0.88 times. So this should be 4.51. 4.151. There. Subtracted from 4.717. Ah, that's it. 566. There we go. Divided by 0.88 is 643.643. That's a calculation error. So this one is going to be 643, and that'll change this value. $83.6. There we go, grams per mole. It all goes back to that right there. That's the question. All right. About out of time. Let's see, we didn't talk about the, we didn't do any pre-labs, did we, for this lab? Okay, so I had you look at the video. Did you look at the video for the pre-lab discussion? You did? Okay, good. At least somebody did. Okay, this one's going to take some time too. So this will be C11 difficult. And it's number 4. Let me see what else is left. Oh, that's it. I'm out of time. All right. What I can do is, well, I don't have time to come back after class. If I do them now, that's going to eat into your lab time. I suppose what I could do is get you started in the lab and come back in here and finish these while you're working the lab. Feel comfortable doing that? Where is everybody? I know Kathy's on the way. Oh,
I'm on my way, but I'm probably gonna be about 10 minutes late.
okay.
I had to stop for gas, and that gas pump was the slowest gas pump ever. It took me almost 20 minutes to put $20 in my gas tank.
My goodness.
1 cent at a time. Like, it didn't go fast. It was like slow.
Was it really cheap gas?
It's 309.
Oh, shouldn't have gone that slow then.
That's what I said.
Okay, so we're actually into Heather. Heather, who's got Heather? Well, until Kathy gets here, we can work a problem or two. Since we're down here at this location, let's go ahead and get this one, number 4. If we have time, we'll go back to that other one. Which I don't understand why it's in the easiest section, because it's not easy. Okay, you have 10.4 gram mixture of table sugar and table salt. So we know that the mixture mass of the mixture is equal to 10.410 grams. When this mixture is dissolved in 150 grams of water, so the mass of water equals 150 grams. I suspect we're going to need kilograms if this is going to be molality. 0.150 kilograms water, because it's mass of solute per, moles of solute per mass of salt. The freezing point is found to be minus 2.24 degrees C. So delta T is equal to 2.24 degrees C. Right, because the freezing point of water is 0. What's the percent by mass of sugar in the original mixture? All right. So if this is the mass of the mixture, and we need to know the percent by mass of sugar, let's let our unknown X be the mass of the sugar. So we're going to let X equal mass of sugar. That means 10.40 grams equals the mass of table salt. All right. So what we've got is this value is actually equal to the influence of sugar dissolved in water and salt dissolved in water. So we're actually going to have 2 expressions here. One, we have to have the Van Hoff correction because salt will dissociate. Then molality times change in temperature. And this is molality for, let's keep it simple. Let's say this is sugar. And this will be for the salt. How's it changing? All right. So we know that for sugar, this one's going to be 1. We don't have to deal with that. This one's going to be 2. The change in temperature. So I'm going to have to cheat it. 11.4. Okay. We are going to need to know the molar mass of each one. So the molar mass of sucrose is 12 times 12.01 plus 22 times 1.01 plus 11 times 16. I guess I better write it down. So we have 12, 22, 11. 12, 22, 11. So this is carbon, 12.01. This is hydrogen, 1.01. This is oxygen, 16. So add them together. Right, and then 22. Add those together, and 16. Add those together. So this should be 342.34 grams per mole. And the molar mass of sugar, salt, sodium chloride, is equal to sodium's 23 and chlorine is 35.45. Right? 23 enter and 35.45 plus. So this is 58.45. All right. Keep myself on track. Oh, wait a minute. My mistake. Sorry. This is K. K freezing point for water, which is 1.86, I believe. That's not in the problem, is it? 1.86. 1.86 here. So the molality of sugar, what we need to know is 1.86 for the KF of water, and then the molality of sugar is going to be the mass of sugar divided by the molar mass. Because if we mass over grams per mole, the grams cancel, we get moles. So this is going to be the mass of sugar, X, divided by 342.34 grams per mole. And the I was 1, so I left that out. This one is going to have an I of 2 for sodium chloride, and then 1.86 for its KF. And then the moles of salt, excuse me, you messed up. This is minus X. So this is 10.40 minus X over 58.45. Okay, and that's all equal to 2.24 degrees C. Now what we have to do is solve for X. All right, and to save time, X should be 5.6 grams. So just work that out, solve for this unknown here, here. And X should be equal to 5.60 grams. sucrose. So percent by mass, percent sucrose is equal to 5.60 divided by 10.40 times 100. And that should be equal to 53.9%. Okay. This is the part I had to skip because it would take too long to solve that on the board. Let's see, we're still waiting on Kathy, so we can do this one next.
Lab is at 10:30, right?
Is it 10:30? Oh,
Just
yeah,
double checking. Okay.
sorry, my mistake. I was cutting off a whole half hour for you guys. Let's go back up to C11 easy 6. I think this is it right here. Here we go. All right, I'm gonna see if I can do this one from memory without having to cheat. Okay, C11. Now we're back to the nominally easy, but it's not really easy. Let me get the marker. This one's starting to crap out on me. Number 6. All right. Solid KF has a lattice energy, that value, and a heat of solution of minus 15 kilojoules. Rubidium fluoride, which is in the same family, potassium fluoride, rubidium fluoride, has those values. Which salt forms stronger attractions with water? All right, what are we given? Well, we're given KF. We're given the lattice energy for KF, which would be K plus gas plus F minus gas yields KF solid. And that delta H lattice energy is minus 804 kilojoules. Massive amount. Rubidium fluoride would be this expression. And its lattice energy is 768. All right, the heat of solution. The heat of solution for KF, delta H solution, is equal to minus 15 kilojoules per mole. And the heat of solution for rubidium is minus 24. Okay, that's what we're given. Which salt forms a stronger attraction with water? All right. If we look at the heat of solution is equal to those 3 steps, delta H1, delta H2, delta H3. See if I get that right. So Yeah. This first one, remember, it's the one where the solute is pulled apart. Right, you got to break those bonds, holding it together. Well, if this is the energy you get when the bonds form, then the energy required to pull them apart is the opposite of that. Change the sign. Right? So what we have here is the heat of solution is equal to negative lattice energy. So let's mark that. Lattice energy. Well, that's going to be a negative value there. All right. This one is the amount of energy it takes to make the hole, pull the water molecules apart. And this is the question. Attraction to water, the solvation energy. Okay. And this one is make a hole. All right. What we can do, since it takes the same amount of energy to make a hole for both of them, then if we combine these two into one value, delta H 23, then we know that the difference between these two, between this one and this one, is due to that one. All right, so all we need to do is calculate what is this value for each one. Okay. So the heat of solution here is minus 15 there. And the lattice, we want the negative lattice energy, which is a negative 804 kilojoules. Let's see, are they all in kilojoules? Our units are correct. Yeah, they're all kilojoules. And this is plus this delta H combined 2 and 3. So this one is going to be negative 768 kilojoules plus its delta H 23. And this is for KF, and this is for rubidium. Okay. So what we're going to do is compare these two. And the one that is more negative is the one that gives up more heat when the solvation occurs. And the more negative means stronger attraction. All right. So the heat of solution for this one here. Okay. So now we can calculate this one, right? If that is a positive on this side, it becomes a negative on this side. So a negative 15 minus 804 is equal to the delta H 23 for KF, which is equal to what? Minus 819 kilojoules. Okay. And this one becomes a positive 768. On this side, it's a negative. So a negative 24 minus 768 equals delta H 3 rubidium fluoride, which is equal to what? Let's see, 4 and 8 is 12, carry the 1 and 8 is 9, 792, minus 792 kilojoules. Right? So these are the values that are assigned to this right here. And the difference is due to that solvation or the attraction. The more negative one is this one. So KF has a stronger attraction to water than rubidium fluoride. Right, so KF, now KF is the right answer, but it's not because of the larger lattice energy. It's because of the more negative heat of hydration. Yeah, they call this the heat of hydration. Heat of hydration. Well, actually, the solvation is the heat of hydration. Solvation is a generic term for any kind of solvent. In our case, we're going into water, which means heat of hydration. Okay,